Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College, and it's my pleasure to welcome everyone here in the Smithwick Theater and everyone viewing us on the web to this lecture in the 17th annual Silicon Valley Astronomy Lecture Series. This series is a free set of lectures in Los Altos Hills, co-sponsored by the NASA Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI, the Search for Extraterrestrial Intelligence Institute in Mountain View. And we're very grateful for the help of all these organizations. It's a great pleasure for me tonight to introduce a very exciting speaker and a very exciting topic. Many of you may have heard that a billionaire here in Silicon Valley has donated $100 million to the University of California at Berkeley to speed up and enhance the search for civilizations out among the stars. And it's a wonderful privilege for all of us tonight to welcome the chief scientist for this project, Dr. Dan Wertheimer. He is not only the chief scientist at the Berkeley SETI Research Center, overseeing SETI at Home, the $100 million Breakthrough Listen project that he'll tell us about, and several other SETI programs. But he also directs the Center for Astronomy Signal Processing and Electronics Research at the University of California at Berkeley, and is associate director of the Berkeley Wireless Research Center. Dr. Wertheimer has been an associate professor in the engineering and physics departments at San Francisco State University, a visiting professor at Beijing Normal University and at the University of St. Charles in Marseille and the Eötvös University in Budapest. He has taught at universities, in addition to this, in Peru, Egypt, Ghana, Ethiopia, Zimbabwe, Uganda, and Kenya. So this is a man who not only knows his way around the skies, but knows his way around the world as well. And he's always been very much dedicated to public education in science, in addition to his scientific work. So, ladies and gentlemen, speaking about Is Anyone Out There Among the Stars?, the $100 million Breakthrough Listen project, it's a great pleasure for me to introduce Dr. Dan Wertheimer.
Well, thank you very much for coming tonight. It's great to see such a big crowd. I want to talk to you about this question, are we alone? Is anybody out there? Before I do, I just want to say a few words about the guy who introduced me. Andy Fracknoy has been, we're just blessed to have him on this planet. He is an amazing science teacher and teaches these critical thinking skills, which I think are crucial for the success of our planet and our democracy. And he's been working on SETI for, I think, 40 years or so. He's on our advisory board. He's on the board of the SETI Institute. And he's did this lecture series, and it's great that he's organized all of us and teaching us about science. So thank you, Andy. So this question, are we alone? I think it's a profound question. People have been asking it for a few 100,000 years, and this may be a kind of special time, a special generation where we might have a chance of answering this question in your lifetimes, and we should start thinking about what the possible scenarios are and how it might affect us and our civilization. I think the answer to the question is profound either way. If we find out that the universe is teeming with life and other civilizations, we could get on the galactic internet. There may be some civilizations that are billions of years ahead of us. You know, our sun is about 5 billion years old. Some stars are 10 billion years old, so we're kind of middle-aged. So there could be very advanced civilizations out there. We could learn what's in our future. SETI is called the archaeology of the future, that we could learn from advanced civilizations how they got through their bottleneck when they were killing each other, when they had nuclear weapons, biological weapons, chemical weapons, Donald Trump. How did they get through that? But I think it's also profound the other way. What if we find out that we are alone? I think that's very interesting, and it means if we're alone, that means life is incredibly precious, and we better take really good care of life on this planet. Okay, so how are we going to answer this question? One possibility is the theoretical approach. This is called the Drake equation, and you can just calculate the number of civilizations in the Milky Way galaxy, and all you have to do is multiply all these things together, and you know how many civilizations in the galaxy. So the problem with this theoretical approach is that we don't have any idea what any of these numbers are. So it's a way of taking a big question, are we alone, and breaking it up into a lot of smaller questions, but also very difficult questions about how many planets are there. So the first part of the equation is about stars and planets. As you go further down the equation, it gets harder and harder to answer the question. We're starting to know about planets in our galaxy. The next thing is in the equation is how many of those planets have the right environment. This little E is for environment. Like how many of them are we call Goldilocks planets, the right temperature where you might have liquid water, not too far away from their star where it's too cold or too close where it's too hot. The right chemicals. Then the next thing, this L is for life. If you have a good planet, a Goldilocks planet, how often does life get started? We really don't know how often that happens. It happened very quickly on Earth, but that doesn't mean necessarily it happens quickly in other places. The next thing is even more unknown. If you get life, this I is for intelligence. So if you get life started on a planet, how often do you get intelligence? That happened a few times here on Earth. It may happen other places, we don't know. The next thing is the C is for communication. If you have intelligence, do they develop communication technologies? Do they have lasers or radio or radar or something, some way that we could detect their presence? And then the last factor is even more unknown. How long do they live? L is for longevity. So I mentioned that our star is a few billion years old. It's going to be around another few billion years. So you could imagine very advanced civilizations that last billions of years. We're just beginning. We're just kind of entering this communicative era where we're just beginning to learn how we might communicate with other civilizations if they're out there. I mentioned that one of the factors in the Drake equation is planets. And if you had asked Andy and me 20 years ago, are there planets going around other stars? We said, well, we think so, but we really don't know. This is a very recent discovery. And the reason it took so long to find out the answer to the question, are there planets going around other stars, is because planets are little dinky things. 1 million Earths could fit inside the sun. And planets don't give off light. And they're right next to this really bright thing. They're next to, it's like looking next to a bright star. It's like looking for a firefly next to a searchlight. So it turned out it was a really hard problem. And only in the last 20 years are we beginning to get a sense of how many planets are out there. And the way they were first found is this depicted in this slide, that they're found indirectly. You can't see the planet, but when the planet goes around the star gets pulled, the planet pulls on the star a little bit. So here's the planet going around the star, and here's the star kind of wiggling a little bit. And if you see a star wiggling, that betrays the presence of a planet. And you can see it wiggling because when the star moves a little bit moves away from you, the colors change a little bit. It's called the Doppler shift. It gets a little redder. When it's moving toward you, it gets a little bluer. And this is a little depiction of how that, you can see that the star is wiggling up and down and over the years. And it's actually got two motions. It's got a kind of quick wiggle and then a slow wiggle. Anybody know why that might happen? Why there would be two kinds of wiggles? Two planets. Good shouting there. Yeah, so there's a planet going around kind of at this speed, and then a planet in closer to the star that's going up and down, moving it quicker. And now we know about stars that have many, many planets. I think there was a recent discovery of one with 7 planets going around it. So this is another way to find planets. This is just a few years old. It's called the Kepler spacecraft. It's a telescope that NASA launched into space. It was built here at Ames Research Center down the road. And it is very hard to see, but this little black dot, if you can see it, in front of this star. So what happens when the planet gets in front of the star is the star dims down a little bit. You can't actually see the planet, but you can see the star dimming down if we're lucky enough to get the planet crosses in front of the star. And what Kepler is it's just a camera, and it looked at a few 100,000 stars looking for this dimming. And the dimming tells you that there's a planet going around, especially if it's a periodic dimming. If you see it dim and then another few years later you see it dim again, or a few days later, depending on how long it takes for the planet to go around. And Kepler found a huge number of planets going around their stars, getting in front of their stars, and the stars would dim. And from the little area that Kepler looked at on the sky, and you extrapolate, if the galaxy is the same everywhere, which we think it is, Kepler found about 3,000 planets. That means that there are about 1 trillion planets in the Milky Way galaxy. That's more planets than there are stars. There's about 5 times more planets than there are stars. A lot of planets, a lot of places for life. This is all brand new in the last few years that we're learning there's tons of places for life. And the other optimistic thing is that some of these planets are in the Goldilocks zone. You might have seen this in the news just last week or a couple weeks ago. The TRAPPIST-1 system is a dim star, but there's 7 planets going around it, and 3 of them are in that Goldilocks zone, not too hot, not too cold, and they're little dinky planets like us, probably rocky planets, maybe liquid water. So anyway, there are a lot of places for life. Well, the next question is, what if you have a good planet? Does life get started? And we don't know exactly how that happened, but here's a little picture. We think it might get started in something called the primordial soup, and maybe in a tide pool or something like that. And people have done experiments where they simulate the early conditions on our planet. So when the Earth was just forming, what they put in here was some methane, ammonia, water, hydrogen, and they also put in some sparks to simulate lightning. We know that lightning was around when the Earth was forming. And you don't get gorillas crawling out of this thing, but you do get the basic building blocks of life, the amino acids, things that you and I are made of, pretty complicated organic molecules. So even though we don't understand the complicated details of how self-replicating molecules, RNA and maybe DNA, formed, we're beginning to understand that process. And as I mentioned, that it happened very quickly on Earth. As soon as the Earth cooled down, life popped up, very simple life. And so the fact that it happened fairly quickly on Earth gives us somewhat optimistic that it might happen quickly on other places as well. There may even be life in our own solar system. Just right next to us is a moon going around Jupiter called Europa. And what's exciting about Europa is that it's got a liquid ocean. So this blue in this cutaway view is a liquid ocean. And one problem is it's covered with ice. So this white stuff here that you see in this artist's depiction is ice, and the ice is about 30 miles thick. And we'd like to find out if there's something swimming around down there in the warm ocean below the ice. And I go to elementary schools and I talk to the kids about how are we going to get through the ice, because we really don't know. How are we going to see if there's something swimming down there? And even in elementary schools, the boys give different answers than the girls. So the boys usually suggest machine guns or bombs. The girls are usually a little more clever. They want to melt their way through with mirrors that focus the sun's radiation onto the ice, or lenses or something like that. But it's interesting that early on there's a difference in how to get through the ice. So there's another moon in our solar system that might make the job a little easier. Maybe we don't need bombs and machine guns. So this is a moon called Enceladus. It's going around Saturn, and it's got the same deal. It's got a liquid ocean. The blue is a liquid ocean, but it's covered with ice. But the nice thing about Enceladus is that there are fissures, cracks in the ice, and there are plumes of water squirting out through the cracks in the ice. And it would be very nice to fly a spacecraft through those plumes, and maybe we could detect if there is some biological, some single-celled creatures or something, so we don't maybe have to bomb our way through the ice in Enceladus. So that's a very exciting mission that the Europeans are thinking about, and NASA as well. Okay, so that's a little bit about primitive life, but I want to talk to you about advanced life and how we might get in touch with advanced civilizations that have a technology, radio or lasers. And you probably know the field is called SETI, which is the search for extraterrestrial intelligence. And Andy and I are not the first people to think about SETI. It goes back a few hundred years, maybe a few thousand years, but Gauss, the mathematician 200 years ago, suggested that we get in touch with ET by making a large geometric structure on the planet, a right triangle, maybe 3, 4, 5 miles on a side, and big square of dirt, big square of water, and big square of wheat, and ET would look down with their big telescope and see that we knew about the Pythagorean theorem. And this was a very clever idea at the time. You might laugh right now, but it's a clever idea at the time. But the unfortunate part of this was a cool idea at the time, but it was not funded. And then Von Littron, also a couple hundred years ago, he suggested that we get in touch with ET by digging a ditch, a circular ditch 20 miles across, and filling the ditch with kerosene, and then use this match, not to scale, to make a bright circle of light, a circle of fire. And again, it was the same idea. ET would look down and see this bright circle of light. I think they were going to turn the fire on and off, put it out, put it on, maybe kind of Morse code. And it was a cool idea. Unfortunately, it met with a kind of similar fate. And the next idea was Charles Crow, almost 200 years ago. He suggested that we get in touch with the Martians by having several mirrors to reflect the sunlight to the Martians. By the way, these are my beautiful art drawings. I was a great art student, as you can tell. So so he had several mirrors, one where he lived in Paris and the others to outline the shape of the Ursa Major. And then the Martians would see these very bright lights from the mirrors reflecting, and maybe they would get in touch. And I think you can guess what happened with that project. So the first funded project was to send pornography into space. Some of you might recognize this. This is a plaque on the Pioneer 10 spacecraft. And on this plaque, this was very controversial, by the way, these two people were originally holding hands, and NASA thought that wasn't a good idea because then ET would think it was one creature, so they don't hold hands anymore. So on the bottom of this plaque is the solar system, and here's the Sun and Mercury and Venus and then Earth, and you can see the spacecraft leaving the Earth. And then here's the spacecraft with the same kind of scale as the humans, and then these are directions to nearby pulsars, so they can find out where we live and come and eat us or do whatever they want. So anyway, that was the first funded SETI project. So one of the big ideas in SETI is that Earthlings send off a lot of radio and television and radar signals out into space. And this is a plot of television power leaving the Earth as a function of time, 1940, 1950, 1960. And you can see the Earth is getting brighter and brighter. This is a logarithmic scale, if you know what that is. And we now have been sending television out for about 70 years. The early TV shows, I Love Lucy and Ed Sullivan Left the Earth 70 years ago, have now gone past about 10,000 stars. And the nearby stars have seen The Simpsons. Luckily, the Donald Trump stuff hasn't gotten to the nearest stars. So we're sending out all this stuff. Radio, FM radio goes right out through the atmosphere, traveling at the speed of light, television, radar signals, GPS navigational signals, all that stuff leaves the Earth. And we've even sent messages intentionally. Almost everything that Earthlings send is this unintentional. The television obviously wasn't meant to go out and go past other planets, but it does. There have been a few intentional messages. These are very controversial. Most people, including Andy and myself, think that it's not a good idea for Earthlings to deliberately transmit messages because we don't know what's out there, and it may be like shouting in a forest, and maybe we'd like to think that other civilizations are peaceful and they're all going to live together happily, but we don't know that. So we think the right thing to do, at least for now, because we're an emerging civilization, is just listen. SETI is just passive. We're listening to see what's out there. But some people think it's a good idea to transmit. And this is an example of a message that was sent in the 70s. And we think a good way to communicate, they're not going to speak English, is pictures. And they're probably going to be able to perceive their environment in 2 or 3 dimensions. And this is an example of this message that was sent. And here you can see the solar system with the Sun and Mercury and Venus, and Earth is tipped toward the person. This is DNA, some amino acids, a telescope. So anyway, it was really meant, I think, as a message more to Earthlings, that we're getting in the game here. We're starting to learn how we might communicate and detect other civilization. We should start thinking about the ramifications. You can imagine if we're sending out signals, then we could also look for signals, which we're doing at Berkeley and at the SETI Institute, and many other groups are looking for these signals. Either we could find an artifact of their technology that wasn't really meant for us, but we could detect maybe something like their television or something. Or, if we're very lucky, maybe a deliberate signal. Maybe they've seen oxygen in our atmosphere. If they're nearby, they've seen I Love Lucy, and they send a deliberate signal. If they send a deliberate signal, I think it will be pretty easy to decode the message. They'll make it anti-cryptographic. They'll have lots of language lessons and pictures and mathematics. If we get some sort of artifact from their civilization, my guess is we'll never quite be able to figure out what they're talking about, but we'll know they're out there, we'll know a little bit about them, but we won't be able to really know much about their civilization. Okay, well, as I mentioned, I'm not the first guy to think about this. The early radio pioneers, the Tesla and Marconi, both did SETI searches. They looked for radio signals from ET, and both of them thought that they found radio signals from ET. And there were big headlines in the newspapers. It turns out they didn't know this at the time, but they were listening to distant lightning bolts thousands of miles away. And the lightning bolts, when it go through the ionosphere, they turn into these whistler noises up. And they heard these chirping noises, and they thought it was ET, but it turned out to be distant lightning bolts. But it was an exciting thing at the time. So at Berkeley, as Andy mentioned, we have a thing called the Berkeley SETI Research Center. And there are about 24 people, students in engineering and physics and computer science and astronomy, and professionals, programmers and astronomers working together to try to answer this question, are we alone? We have funding from the Breakthrough Foundation, which is not very far from here, and that's called the Breakthrough Listen Project, which I'll tell you about. We also have some funding from the National Science Foundation and from NASA and from individual donors, and also some companies that are mostly nearby here who are helping us out by donating equipment and some of the chips and things that we use. We have a lot of different experiments that we're doing, looking for radio signals and also looking for laser signals in the infrared and at visible wavelengths. We're trying to cover try to do a lot of different experiments because it's very hard to predict what ET might be doing. But mostly it's looking for technology. We call them techno-signatures, either the kind of things that are transmitted by AM or FM radio or maybe lasers. We're looking for kind of either artifacts or maybe deliberate kind of signals from their technology. So one of the problems in SETI is that we don't know what frequency ET might be transmitting at. We don't know what channel. And what you want to do in SETI is look at as many frequencies as you can, as many channels as you can. And in the early days of SETI, we couldn't look at very much of the spectrum, of the radio spectrum, and so we had to kind of guess where ET would be transmitting. And we thought a good place to look was this thing called the microwave window, frequencies between about 1 and 10 gigahertz, where the universe is very quiet. If you tune your radio in that region of the radio spectrum, you'll hear a kind of static, but it's quite quiet, and so ET wouldn't have to turn up their transmitting power. We could detect them relatively easy because it's a quiet place in the spectrum. It's called the microwave window. Now we're branching out a little bit, and we're searching at many places in the electromagnetic spectrum, not just searching for radio waves. We have different telescopes at radio wavelengths, but also we think lasers might be a good way to communicate, infrared lasers or visible lasers. There's lots of pros and cons. We don't know what wavelength or what frequency, what channel ET might be transmitting on, if they're transmitting at all. So we're trying to branch out and do different searches using different kinds of telescopes at different frequencies. Well, the very first project that we did in SETI at Berkeley was funded by NASA. And NASA requires that you use acronyms. So our first project is called SERENDIP, Search for Extraterrestrial Radio Emissions from Nearby Developed Intelligent Populations. And the very first telescope that we used is located in Northern California near Mount Lassen. It's called the Hat Creek Radio Observatory. It's this dish. This is a radio telescope, a big radio antenna to look for these signals. We used this in the 70s, and this is about 85 feet across. And while we were using this antenna to look for radio signals from ET, this is what happened to that telescope. So this is the dish. It used to be up here on this pedestal. And okay, we said, well, we can't use that antenna anymore, so we went to this telescope. This is a bigger telescope. It's 300 feet across. And I don't know if you can see, but there's a full-size jogger down here. This is in Green Bank, West Virginia. And while we were using this telescope to look for ET, this is what happened to that telescope. And you might ask, why is this happening to Dan and his colleagues at Berkeley? And we were wondering about that, and then the answer, according to the World Weekly News, is that the aliens did not want to be discovered. This is the headline, "Zapped by Hostile Space Aliens." So they destroy these two telescopes to keep us from discovering them. So that's an interesting idea, and we are testing this ZAP theory at this telescope. So some of you might recognize this. This is the world's largest radio telescope, although the Chinese are building a bigger one right now. But this thing is in Arecibo, Puerto Rico. It's called the Arecibo Telescope, and it is 1,000 feet across, and it holds about 10 billion bowls of cornflakes, although we haven't actually tried that. So this doesn't look shiny to you, but if you're a radio wave, it's got an aluminum surface, and the radio waves bounce off this mirror, and they're collected at a focus up here. And we've got equipment that's running at this telescope 24 hours a day while astronomers are pointing it to whatever they want to point it at, galaxies, stars. They're studying all kinds of things. We go along for a ride looking for ET. So we don't usually use this telescope just to ourselves. We don't get to point it. We let other people point it, but we don't know where to look anyway. So that works out pretty well. But so far, it hasn't been zapped by hostile space aliens, but it is kind of built into the ground. You might have seen this telescope in James Bond, GoldenEye. It was in that movie. They show it coming up out of the water, which it doesn't do, and they say it's in Cuba, which it isn't. But the other movie that it was featured in that you might have seen is a movie called Contact, which was originally a book written by Carl Sagan. And it's a great book and a great movie. I recommend it if you haven't seen it. And the only difference between that movie and real life is that Jodie Foster finds E.T. and we haven't. But other than that, it's a pretty accurate description. Carl Sagan worked in our group for about a year. He took a sabbatical with us, so he's an expert on SETI. I wanted to tell you about this new project that we're doing that Annie mentioned, the Breakthrough Listen SETI project, and it is spectacular. It's beyond our wildest dreams, and we just launched it about a year ago. We're just getting started on this thing, but it's way bigger than anything that we've ever done or anybody's ever done. We expect to spend $100 million over 10 years, $10 million a year. We're starting with 3 telescopes, a couple of radio telescopes I'll show you, and an optical telescope to look for laser signals. The one we're using is at Lick Observatory, which is right near here, about an hour up in Mount Hamilton. Some of you may have been there. If you haven't been there, I recommend. It's a beautiful drive, and they have evenings where you can look through the telescope and see what's going on up there. We're planning to do 1 million stars, but we're just getting started and look at whole thousands of galaxies. And I'll tell you a little bit about what's going on with this new project. So these are the 3 telescopes that we're starting with. This is the one that's looking for laser signals. It's called the Automatic Planet Finder, which is usually used to search for new planets, but we're also using it to search for laser signals from other civilizations. And that's the one at Lick Observatory, which is right near here on Mount Hamilton. And then we've also used this Green Bank Observatory. So that telescope that I showed you that collapsed, the big one, when that collapsed, there was a very powerful senator in West Virginia, and he said, I want to build an even bigger telescope. So this is called the Robert Byrd Green Bank Telescope. And we've got a lot of telescope time. So before, when we were doing setting, before Breakthrough Listen, one of the big problems is it was very hard to get telescope time. Everybody wants to use these huge telescopes, and we're lucky if you get a day or 2 a year on these telescopes. But now we got a huge amount of time on these telescopes, so we can really do a much more thorough search, point the telescope where we want it, nearby stars, and look at a lot of different frequencies. So that's a huge change for us. And we've also got a lot of time on this Parkes telescope, which is in Australia. The reason that it's important to have a telescope in the southern hemisphere is because these two can only see the stars in the northern hemisphere, a little bit in the south, but not if you go way down. And there's a lot of interesting things in the south. Those are the very nearest star you can only see from the star Alpha Centauri. The center of the galaxy you can only see from the southern hemisphere. So most of SETI projects that we and other people have been done from the northern part of the sky, because that's where most telescopes are. But anyway, this will be a new thing for us, is to look at some of the southern stars and galaxies and other things in the south. And as I mentioned, we're planning to look at 1 million stars, although we're just getting started. and 1,000 galaxies. So it's a very ambitious project. These are the stars that we've looked at so far. We're just now getting started looking in the south. So you see most of these stars are in the northern part of the sky, the ones that we've done so far. And we've looked at about a little more than 1,000 stars. The different colors are the different kinds of stars, whether indicating the temperature of the star. Some are hotter than our sun, some are colder than our sun. Anyway, so we're learning how to do this, and it's an ambitious program. This is an example of the data that's coming from the observatory that's looking for laser signals. And this is the kind of thing that gets our attention. It's a narrow signal at some frequency or some wavelength. That's what you might see from a laser from a distant civilization. And unfortunately, I wish I could tell you we found ET, but we know it's not a laser signal because when you look closely at the CCD image, it's coming in at an angle, and that turned out to be a cosmic ray. It turns out occasionally the CCDs can detect these cosmic rays coming from other places in the sky. And luckily, when the cosmic rays come in, you can usually figure it out because they come in at some weird angle where you'd expect the laser line to be kind of vertical on the CCD. And so we can kind of tell the difference between these false alarms from cosmic rays. So far, no signals from ET. If you are good at computers or interested in this, there's a lot of data that we are collecting in this new project, the LISTEN SETI program. And we're trying to make the data available we've got a big website and places where you can look at this data and help us figure out how to analyze it. We've got examples of software that we use and examples of how you can read the data. And we're trying to get people, especially people who have some computing skills or interested in data analysis. We want to get the community involved, not just the scientific community, but I think a lot of people around here in Silicon Valley have a lot of skills that we'd hope to get people involved. I want to tell you a little bit about the kind of signals that we look for. So I mentioned that one of the big problems in SETI is we don't know what frequency ET might be broadcasting on. So what this plot is how strong the signals are at different frequencies. This is frequency number 2,264,191. This is frequency, I can't read it, but anyway, it's 2,264,959. And here, at this frequency, is a strong signal. That's the kind of thing that gets our attention. It's like kind of tuning your radio dial across the spectrum, and you're looking at the signal strength meter, and at some channel, some frequency, the signal strength meter goes up. That's what we're seeing here. It's a little different than tuning the radio dial because what we want to do is listen to many, many channels at once. So this is like having millions of radios on your desk, each one tuned to a different frequency. So you don't have to tune here, then here, then here, like a police scanner, one channel at a time, but you can listen to a whole bunch at once. So it just speeds up the process. Anyway, that's the kind of thing that we're looking for. And I wish I could tell you that was ET, but it was a satellite going over the telescope. And there's a big problem in SETI that we're looking for radio signals from extraterrestrials, but we find a lot of radio signals from terrestrials. We call it radio frequency pollution or radio frequency interference. And these telescopes are usually far away from people, and Green Bank, West Virginia is far away from civilization, but civilization is encroaching and people have transmitters and cell phones in their pocket. You're not supposed to use cell phones when you're near Green Bank, but people do, or they have wireless or something. Cameras give off radiation. Satellites fly over, and it's getting harder and harder to do SETI from the Earth. We may eventually have to do SETI from the backside of the moon, where the moon would act like a big shield from all the radio pollution and television pollution, radar signals coming from the Earth. That will be incredibly expensive if we have to move to the moon to do these kind of experiments. So this may be a kind of unique window in our history where we have the kind of technology, or at least we're developing the kind of technology where we might be able to detect ET, and we can do it from the surface of the planet with these ground-based radio telescopes that are relatively cheap. If we have to go to the backside of the moon, that's going to be really expensive, maybe unaffordable. Another kind of signal that we look for to discriminate between whether the signal is from Earth, terrestrial interference, radio frequency interference, radio pollution, or whether it might be coming from ET, is what we do is we point the telescope to a star, and then for a few minutes, and then we move away from the star, and then we go back to the star, and then we move away from the star, and then we go back. And we do that 3 times, this kind of off, on, off, on, off, on. And then we see, did we only see the signal when we were pointing at the star? And you can see there's something that got our attention here. You can see this yellow stuff. And we only saw it when the telescope was pointed to the star. We did not see it when we moved away from the star. And that gets our attention because it's probably not coming from a television station, which you'd expect to be kind of on no matter where you're pointing the telescope. So that's one way we can discriminate against this radio pollution problem, but it's not a great way. It's getting harder and harder to do this. Another kind of signal that we want to look for is what we call a drifting signal. And these are examples of drifting signals that are changing in frequency. This one's going, and this one's going the other way. Now, why would that happen? If a transmitter is on a planet that's spinning around or going around a star, that introduces an acceleration. It's called a Doppler shift. Some of you may know about that. And even if the transmitter itself is at a constant frequency, the way that it would come to our telescope is because of this acceleration, because of the movement of the transmitter, you'd get this chirping signal. And we don't know what frequency, and we don't know the slope, how it would be chirping. So we want to look for these kind of things. And you can see them with your eye, I think, pretty easily. You can see these patterns. But we have about 100 million of these things to look at every second. We have a lot of data to go through to look for these kind of chirping or drifting signals. Another thing that we want to look for is a pulsing signal. And this is a bip, 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 bip. And I've circled them here, and it's pretty easy for you to see it when I've circled them. But if I remove those circles, it's actually pretty hard for your eye to find that repeating pattern. And it's pretty easy for computers to do this, to look for these repeating pulses, but we have about 100 million of these things to look at every second. So we need a lot of computing power to look for these different kinds of signals. And one of the projects that we're doing to how to kind of gather a lot of computing power is to ask people around the world that have laptop computers or desktop computers if they can help us analyze the data. And some of you may know about this project. It's called the SETI at Home project. Anybody here running the SETI at Home project? Oh, great. A lot of you already know about this. You can go to sleep for the next couple of minutes. So the way the SETI at Home works is we record data at Arecibo, or now we're using the Green Bank and the Parkes Telescope in Australia. And we take that data and we break it up into little pieces. Everybody gets a different part of the sky to work on. And then we record it at the National Energy Supercomputing Center. And then we have about a couple of petabytes of data. And then we send that data out to volunteers around the world. If you have a computer, or now you can actually do it on your phone, you can help us analyze data from the world's largest telescope if you have an Android phone. And what you do is you download the SETI at Home screensaver. And it's not just an ordinary screensaver. It doesn't just put up pretty pictures of goldfish swimming around on your screen. When you go out for a cup of coffee, the screensaver pops up. This is a free program, by the way. You can download Google SETI, and you'll find the SETI at Home project. You can download it. Then when it pops up on your screen, what it does is it connects to our computer at Berkeley, and over the internet, you'll get one of these chunks of data recorded at the world's largest telescope. You'll get one part of the sky, somebody else will get a different part of the sky, everybody gets a different chunk of data. And then what it does is it goes through all that data, looking at all the different frequencies for those pulsing waveforms and drifting waveforms, and all the different kinds of signal types, looking for something that might be interesting. On the screen, it reminds you kind of what part of the sky you're looking at and what frequency band you're looking at. It reminds you what your name is and how much work you've done. And then it shows you the most interesting signals. And when it's finished analyzing that piece of data, we call it a work unit that you've been assigned, it might take a few days. Then it'll send the results of that data analysis back to our computer at Berkeley. And your name is attached. So if you find ET, then you might get the Nobel Prize, although I don't make that decision. So we've got a lot of people helping us analyzing this data from these three telescopes. This is a little animation of the data coming out from Berkeley. The yellow dots are different parts of the sky that we're sending out. We call them the work units, out to the volunteers around the world. And then when they're done analyzing the data, the blue dots are going over the internet, sending the results of that data analysis from their home computers back to Berkeley, where we build up a big database and try to figure out what's interesting and what we should go back and look at, and who should get the Nobel Prize. So now I said you might get the Nobel Prize, but I wanted to warn you that you might not get rich, because there are about 8 million people who have downloaded the SETI at Home screensaver. The Nobel Prize is about $1.5 million. If you have to split it with all these volunteers in 226 countries, it's, I don't know, about 20 cents per person. So we're very grateful to the people here and others who are participating in SETI at Home. They built one of the biggest supercomputers on the planet. They donated 1,000 years of computing time a day. That means if we had just a single computer, it would take us 1,000 years to do what the volunteers do in one day for us. And it's made the search incredibly powerful, much more sensitive than anything we could have used. It looks for a lot of different signal types. And so I would encourage you, if you're interested in SETI, to help us in this hunt for other civilizations and download the SETI at Home screensaver. If you want, you don't have to do this, but if you want to participate in SETI at Home, an optional thing is to join a team, and there are thousands of teams, primary, junior colleges, universities, small, medium, large-sized companies. And the teams, you can make your own team. You can make the Foothill College team. The teams compete with each other in somewhat friendly ways. Here's Intel has donated 1,300 years, and Microsoft has donated 2,000 years. And this competition has led to some interesting behavior. Some people build these big computers in their basements that are clusters of very fast computers so that their names will bubble up near the top of the website. They'll get a lot of credit. And you can go to this website called setifarm.org, and you can see these guys, and they're all guys. As far as I can figure out, there are no women that do this. Here's another guy computing with his SETI cluster. I don't know why he's got these bolt cutters with it in that pose. So anyway, this has been a great project for SETI because it's made the search very powerful and it's gotten the public involved. And even though we haven't found ET, one of the things I'm happy about is that a lot of kids are running this in schools. And this question, are we alone, is something that a lot of kids are interested in. And it touches on all different areas. As you address this question, you can get the kids interested in astronomy and evolution and how does life get started, and chemistry and physics. It touches on a lot of different areas in science. And we developed a curriculum with the Lawrence Hall of Science to try to get kids engaged while they participate in SETI at Home, thinking about this question, are we alone, and learning about different aspects of the sciences that it touches on. The SETI at Home project led us to kind of branch out and think about not just using your home computer to do SETI, but could you use your home computer to do other kinds of scientific supercomputing projects? And we developed this software, open source software, so that you can now use your home computer to participate in 100 different science projects. You can look for cancer drugs or HIV drugs or malaria drugs. You can do global warming research on your home computer. You can find new planets there, and you can allocate how you want your spare computing cycles to be used. You can say you want 30% of your spare computing time to do SETI and 20% for malaria drugs. You pick your favorite projects. This is SETI at Home. This is climate prediction. This is gravity wave, looking for new pulsars. This is something called Astropulse, looking for fast radio bursts. This is protein folding, and you can participate in the projects that you're interested in. And the idea is kind of the democratization of scientific computing power. And there are a billion kind of computers out there, and a lot of it turns out most of the computing power on the planet is in the small computers. It's the computers that you and I own, or in the things that are in your pocket right now. And it's called edge resource aggregation. We get a lot of people participating. You'd think that the supercomputing is really in these giant centers where there are supercomputers, but that's not true. It's the stuff that you and I own. That project's volunteer computing led us to also think about using the public to do things that computers are not very good at. It turns out computers are not very good at pattern recognition, things that your eye and brains are good at. Our first project, we call it Thinking at Home, we did a project called Stardust at Home. This was a spacecraft that we worked on with NASA to go out near a comet and scoop up some of the dust in the comet's tail. And we also scooped up some of the dust that was around 4.5 billion years ago when the planets were forming, to see how the planets were forming. And this spacecraft, the Stardust spacecraft, came back, landed, it's a sample return mission, landed in the desert in Utah on a parachute, and we brought the samples back to our lab, and they're little microscopic particles from 4.5 billion years old when the planets were forming, and there are also particles in that aerogel foam in our lab that are from the comet that we flew through, and we wanted to find these particles in the aerogel foam, the thing that scooped it up, and then we wanted to figure out what they're made of. And it turned out finding these little microscopic particles in these big sheets of aerogel was a big problem. We thought we would need thousands of students looking through thousands of microscopes for years. What we did is we made millions and millions of photographs on this automated microscope. It can move around in different focus depths, and we sent these photographs out to the public, and you can help us find the little dust particles. It's called Stardust at Home. And you do a little training, what the particles look like, and then you run this kind of virtual microscope on your home computer. And we had about 70,000 people sign up, and they found particles. We're still running it if you want to participate. Particles that we never would have found if we just did it at Berkeley. And we're beginning to learn from this how the planets formed and how these dust particles stuck together, and a little bit about how comets are made and how the tail and the nucleus forms. And this is all due to kind of citizen science. And now there are a lot of citizen science projects, not just our projects, but many different things that you can participate in. I want to get back to SETI for a second. I want to say some of the new things that we're working on. This project is called Interplanetary Eavesdropping. And the idea is if two planets, if there's are machines or beings on two planets, they might be sending messages back and forth. And now with the Kepler spacecraft, we know exactly when these two planets are in line with Earth. And if there are messages going back and forth between two exoplanets, we can schedule our observations and point and maybe intercept communication going back and forth. Like right now, you know that there are rovers going around on Mars and there's communication between Mars and Earth. Maybe there's something like that in a distant exoplanet, communication going back and forth, and we're trying to intercept those kind of messages, scheduling it when those two planets are in line. This is the project we're doing at Lick Observatory, not too far from here, looking for laser signals. That's Frank Drake from the Drake equation, and Shelley Wright is now a professor at UC San Diego. That's me in my youth, and the director of the observatory, Rem Stone. We're also looking for infrared signals. This is a project that was built by Charlie Towns, who invented the laser, got a Nobel Prize. He died recently at 99.52. We round up to 100. And Charlie, when he invented the laser, he thought it would be a good idea might be a good way to communicate between the stars. And at the time, lasers, when he invented the laser, lasers were little things like this laser pointer, not very powerful, but now they're big lasers that could easily communicate across the galaxy. So we're trying to follow up on Charlie's ideas. Well, we haven't found ET. And I'm a little uncomfortable with bragging about SETI spin-offs. It's like NASA saying, give us more money because we invented Tang and Velcro. But we haven't found ET, so all I can talk about are kind of what have we found on the way, these spin-offs. And we have found some interesting things. So one of the things that we found, it turned out the instruments that we developed for SETI turned out to be very valuable in radio astronomy, and we made a bunch of discoveries, or other people have used these instruments to find. One of the things that they found are these things called fast radio bursts that we don't understand. It's a whole new phenomena. They're extremely powerful explosions, and they're the brightest thing in the universe. They last 1,000th of a second. They come from 1 billion light years away. We don't really know what's causing them, but we think they're going to be very useful to try to understand the universe. We think we can actually use these fast radio bursts to weigh the cosmos, to measure the density, the baryon density of the cosmos, because they're these extremely bright, powerful pulses, and the way they propagate through the intergalactic medium as they come to us tells us something about what's between us and these distant galaxies. Another thing we found, or actually I shouldn't say we, but the instruments that we developed originally for SETI were used by our colleagues to find a planet made out of solid diamond. My wife is very interested in this discovery. We used the instruments that we developed to make the first maps of the black hole at the center of our galaxy. So these instruments have turned out to be very useful. The most massive pulsar, a lot of new discoveries have been made with the instrumentation we developed. They also, mostly they've been used in astronomy, but recently they've been used in other fields, in medical imaging, and we use the SETI instruments to get data out of somebody's brain, and we hope eventually that can be used to control a prosthetic arm with an implant that will with a radio link, and you can control a prosthetic arm. That's kind of distant research, but we're using the SETI instruments to learn how to get data out of somebody's brain with an embedded array. I want to say a few words about what we're thinking about kind of long-term for future SETI experiments. So one of the things that we want to do is use bigger, even bigger telescopes, because the signals are likely to be very weak, and so you need a big telescope. So it turns out China is building this huge thing, bigger than Arecibo. It's called the FAST. It's a 500 meters across. The Arecibo telescope is 300 meters. It's made out of thousands of aluminum panels, and they just finished building the thing, and we are working with them to try to get a SETI experiment there. We're actually going to do a survey where we scan the sky, and while we're kind of raster scanning the sky, we're going to be doing lots of things, looking for new pulsars, making a map of the hydrogen in the galaxy, looking for these new fast radio bursts that we don't understand, and at the same time looking for radio signals from ET. So we're going to do 5 experiments simultaneously, all sharing the sky, scanning the sky together. Another new thing that I'm excited about is instead of one giant dish, we are learning how to build telescopes out of lots of little dishes. And the SETI Institute in Berkeley developed kind of the pioneering prototype of this, where we put together 42 dishes, and now we're building something in South Africa with 352 dishes. We haven't built this yet. We've got 39 dishes. Each one of them is 14 meters. But this is kind of a new way to build big telescopes. Instead of building them as huge dishes, you make them out of lots of little dishes. You can stamp them out like hot tubs. We think this is kind of the future of radio astronomy. And so we're building this now. We just got funded from the National Science Foundation and from the Gordon and Betty Moore Foundation to build this. We're not building it for SETI specifically. We're building it to understand how the first stars and galaxies formed 10 billion years ago. But we'll also try to do some SETI experiments on this telescope. And that's leading up, that's a prototype for this thing called the Square Kilometer Array, which is a huge international project that'll probably have 4,000 dishes and will be built over the next decade or so. And we're just starting to get mostly the Europeans and the South Africans and the Australians, a little bit of the US, but that's a grand vision for SETI, is this huge international telescope that will be built in Australia and in the desert in South Africa, away from people and their transmitters. So we haven't found signals. There's no evidence of ET yet, but I'm optimistic that if there are signals out there, that this might happen in the near future. And the reason I'm optimistic, so I've been looking for ET for 40 years now, a little longer. The reason I'm optimistic is we're not doing the same experiment that we did 40 years ago. So in the 70s, I built a thing that I was very proud of at the time that had 100 channels. I was in the Homebrew Computer Club with Steve Jobs and Steve Wozniak, and I learned how to build these things. And everybody in that club got rich except me, because I was interested in using these new computer chips to do SETI. I didn't think about building something that other people could use and I could sell. But anyway, so I built this thing that could listen to 100 channels. I'm very proud of it. And at the time, it seemed like better than anybody else. And then we built in the 80, 65,000 channels, and then 4 million channels, and now we're up to about 100 billion channels. Not because I'm getting smarter. It's all coming out of Silicon Valley, right around here, all these companies. And this Moore's Law has made the instruments more and more powerful, almost by a factor of 2 every year, this geometric increase, an amazing increase in capabilities in computing and SETI. The telescopes are getting better, but mostly it's the computing power. This is a graph of computing power as a function of time, and you can see right now computers are as smart as a lizard or a guppy. But if this trend keeps growing, this exponential trend, it's been going on for a long time. It's an economic law. It's not a physics law. But if it keeps going and people keep investing in Silicon Valley, then computers will be as smart as humans in 2030 or 2040. That's called the singularity. It'll be very good for SETI. We'll be able to do much more thorough searches and see if there are these radio or optical signals out there. It might not be good for humanity when computers can start designing themselves and they get faster and faster, but it'll be good for SETI. But we should be careful about what might happen in our future when computers are that smart. Okay, so in the long run, there are some even bolder ideas. So one of the ideas, but this is maybe 100 years away, is that you could build a huge telescope if you could use the sun as a lens. So the sun has gravity, and Einstein predicted this 100 years ago, that the sun works like a lens and collects the waves, either radio waves or light waves, and they come to a focus, and you could use the sun as a huge telescope, as a gravitational lens. That would be way bigger than anything we've got on this planet, a telescope the size of the sun. Now, there's a problem, is that the focus is way out beyond Pluto. You got to put the camera out there. We don't know how to do that. But if we could do that, you could read license plates on an extrasolar planet. So don't hold your breath on that. That's, for your kids or your kids' kids. Anyway, I'm optimistic that if there are signals out there from other civilizations, either artifacts of their technology or maybe, I doubt this, but maybe they're deliberately sending a signal, but I think artifacts that may happen in our lifetimes. So I'm optimistic in the long run. I'm optimistic about life out there. I think it would be kind of bizarre if we're the only ones, but we really won't know until we're searching, and I think Earthlings are just learning how to do it. This is a very exciting time where we have a chance of finding out the answer to this question, are we alone? Well, if you've been asleep, I have one slide for you. Here's kind of a summary slide. So, no ET so far, still working on it. So that's kind of the summary of this whole talk, but I'm not done. I got three more slides I want to show you. So, kind of a fun thing in SETI at Home is there are a lot of people that want to help us out, and they have a lot of really cool ideas of how to do this. It's a big open source project, and they help us write the code and add new features and new ways to look for signals and speed it up, and they get the bugs out of the code, and they send us money. Some people help us, which funds the students and the people that work on it, and they give us equipment. Some people do writing about SETI, or they compose music about SETI, and some people send us haikus and there are thousands of haikus that people have sent us. But don't worry, I'm not going to read you thousands of haikus. I just want to read you a couple. And this is, the first haiku is from Paula Cook at Duke University. Searching for life, answers are revealed about ourselves. And this is the last slide and the last haiku. Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. Well, thank you very much. Here, please.
Hi. I just had a question about power, I guess. For the telescopes that we have today, are we able to pick up artifacts equivalent to the power that the Earth is emitting at any reasonable distance?
Yeah, that's a really interesting question. So Earth sends off a lot of different kinds of signals. It turns out that the television signals that we transmit are not very powerful, and they would need a really big telescope, and they would have to be pretty close to detect them. Now, we transmit things that are much more powerful. One of the things that Earthlings transmit are something called BMEWS, ballistic missile early warning radar systems. The Russians have these to look for incoming missiles. The US has them in Alaska to look for incoming missiles. And these things are a little more powerful because they sweep across the sky, so they're kind of in a fan beam. And those would be easier to detect. We've been sending those for about 50 years. And then the most powerful thing that Earthlings send is that big telescope that I showed you, the Arecibo dish, the biggest telescope on the planet, although China's building a bigger one, but that thing that's 1,000 feet across, it not only can listen, it's not only just a receiver, but it's got a transmitter, although it wasn't meant for SETI. It was meant to bounce signals off asteroids and study the atmosphere and planets. But that transmitter could be seen. It's a megawatt transmitter connected to a huge telescope. That could be seen, detected on the other side of the galaxy. That's 100,000 light years away. So if Arecibo sent a message, and then you'd have to wait 100,000 years, it would go across the galaxy. If they had an Arecibo on the other side of the galaxy, they could detect that. But it's not the kind of communication between individuals. It's not like, hi, how's your mom? It's like, here's our Library of Congress, all our music, poetry, literature, medicine, please send us yours. because these messages to that far take a long time.
Thank you.
Follow-up to that question, I guess, is do we lose some of the information in those signals? Do they dissipate?
Yeah. So these signals do get weaker. They never stop. They go out at the speed of light, but they get weaker and weaker as they expand and have to cover a larger volume or area of the sphere. As they get weaker and weaker, they get weaker with the square of the distance. It's the inverse square law. And so the further away you are, the bigger telescope you need, or you have to stare at it longer. But they keep traveling at the speed of light. They can't be recalled. Be careful what you say when you're on TV or radio.
I think, remember, for the movie, there was the government was funding this, and then somebody in the Congress said, well, you can't do that because we know the world is only 6,000 years old. Why are we doing this? Is there any government funding? And the second question, is there any pushback from the anti-science community?
Yeah, so the government funding has been kind of on and off. In 1992, SETI was given the Golden Fleece Award. There was a Senator Proxmire, and then there was a guy, Senator Bryan from Nevada. And at the time, they wanted to say that they were cutting costs. You know, they pointed to expensive toilet seats on aircraft, and they thought SETI, the search for, I think they called it a hunt for little green men or something like that. It was nothing in the NASA budget. It was, you know, it was a penny a person or something or less. But it was an example of something that they thought was frivolous, and the funding went away for a while. So the government funding comes and goes, and we've had pretty good luck getting some modest funding from the National Science Foundation and from NASA. And then there's private funding, and that comes and goes depending on the economy and who's interested. But we're extremely lucky now to have our neighbor who owns a mountain nearby. He is one of the key guys behind the Breakthrough Foundation. That they give away these breakthrough prizes, like Nobel Prizes, and their very first science project that they're funding is the Breakthrough Listen SETI program. And now they're starting to fund other science projects as well. You might have heard the Starshot project, try to get a spacecraft to the nearest star at the 20% the speed of light. Very exciting. So they've got some they like to fund these very high risk, high reward, ambitious science projects. We're very lucky. We kind of struck gold. It's a spectacular new program.
Second question was, any pushback from the anti-science community?
Oh, so I think, you guys might know better, but my sense is that the public is excited about this question, are we alone? And most of the public thinks it's good because it's not very expensive, as I mentioned, less than a penny a person, and most people would be happy to have a little bit of their tax money to go for this kind of interesting question. There are a few people that think it's a waste of time. There's a small minority of scientists. Most of the scientists think it's a good idea to do this, to do these kind of searches. But there are a few people that think that life is either unique on this planet or incredibly rare, that the biological processes are just, there's something very unusual that happened on Earth, and we don't really know, but some people think, and sometimes it's a religious motivation. A lot of religions, I think, are comfortable with this idea that life could be elsewhere, and we used to think that God only kind of looked after life on this planet, but I think a lot of religions are comfortable with this concept that there could be life on a lot of places, and it's not so geocentric.
Let me tell you what I think I heard tonight and see whether you agree. Previously, I'd thought of SETI as being kind of separate from other astronomical activity, but what I think I heard is that what we're really looking for with SETI and the rest of astronomy is any kind of signals or information from space that can really be thought of as an integrated part of astronomical research. Would you agree with that statement?
Yeah, I guess I kind of half agree with what you just suggested. I mean, we are looking for very specific kinds of signals, but we work very closely with other astronomers that are making maps of the galaxy, looking at pulsars, looking at gravitational waves, and all this technology that we developed for SETI is starting to get used by a lot of people. So we're in very close collaboration with other astronomers who either use our data to make maps of the galaxy, or we use their data. And so we're tightly integrated into the astronomy community.
Thank you.
Dan, thanks for a very interesting talk. I have one question. Let's be optimistic and assume in our lifetime we detect extraterrestrial intelligence signal. I'd imagine you guys have thought about it for quite a while. What would be the protocol, and how would that be announced, or would the government immediately classify it with Project Blue Book or something else?
So there is a protocol that we and other groups have signed, but the protocol is just kind of the first part. And the first part of the protocol is that before you make a big announcement, gain some confidence that you found something interesting. Because we find a signal, it might be like a bug in our software, or something wrong with the equipment, a graduate student playing a prank on us or something like that. So what the protocol says is, before you make an announcement, ask a different group to see if they can detect it as well. A different group, different people, different telescope, different software, different equipment. And if you have two telescopes looking at it, you can kind of triangulate on it and measure the distance to the thing and make sure it's not something that is man-made, that's a satellite or something that was built by humanity. And we know at that point that it is a very distant signal, that it doesn't come from a human origin. Now, we might not know it's from another civilization. Some of you might know the story of Jocelyn Bell, who discovered, she didn't know it at the time, she discovered this whole new phenomena called pulsars. And at the time, they were called LGM1, LGM2, Little Green Man 1, Little Green Man 2. They didn't know what they were. They turned out to be a whole new, very exciting astrophysical phenomenon. So I can imagine we discover some new kind of signal that hadn't been anticipated, and we will be we're not sure. So I think if we can get two independent confirmation from another group, what we will do, and what other groups have agreed to do, is that we will, at that point, publish everything we know about the signal on the web and other places, the coordinates, the frequencies, any kind of data that we've gathered. But we probably won't say, this is definitely, give us the Nobel Prize, we found ET. It'll be, we probably say we found a really interesting signal, we don't know what it is, it might be a new civilization, it might be some new astrophysical phenomena. And then at that point, I think people from all over the world will start looking at this, because we can't track it with our own telescope, the Earth is rotating, other people start looking at it, and hopefully everybody will share data and try to figure out what this thing is.
Thank you.
Thank you for a talk that was not only interesting, but also very comfortable. It turns out decades ago, I heard Francis Drake give a talk and introduce his equation, and it's clear that the factor F sub p has changed substantially since he gave that talk. Do you know how much that factor has actually changed, and have any others changed as dramatically, either up or down in magnitude?
Yeah, so in the Drake equation, as you pointed out, one of the very first factors is how many planets are there. And at the time that Frank Drake put that equation together in the 60s to organize a conference, nobody knew how many planets. We knew about planets going around other stars, but we had no idea whether there were other planets going around other stars. So now we know that planets are more common than stars, and there are even lots of good planets. There are billions of good planets in our own Milky Way galaxy. There are 100 billion other galaxies. So that factor is kind of the only one that we really know about now, about how many planets are. That is the one factor in the Drake equation that astronomers pretty much agree on, how many planets there are and how many are at a good distance from their sun. And we know a little bit about how many rocky planets, but we don't know how many planets have the right conditions, the right chemicals for life. Do they have liquid water, all the right things that make up you and me? So we're, unfortunately, the Drake equation, the rest of the factors in the Drake equation, we still really don't know, and the only way to solve this problem is to go out and look. We can't really get at it from the Drake equation. But you're right about the planet thing. We do, after Frank wrote this equation, we finally got that very first factor pretty well pinned down.
Thank you for a very interesting talk. Now, I think I heard you say that you're more optimistic about overhearing a communication than receiving a signal deliberately broadcast. The little ET's basically saying, yes, we're here. Now, the trend in communication seems to be towards spread spectrum and encoding and encryption and all these things. So to paraphrase Arthur Clarke, it seems to me any sufficiently advanced communication is indistinguishable from noise.
Yeah, so that's a very astute question. I bet you're a Silicon Valley radio engineer. If you go back to that plot that I showed of the radio power leaving the Earth, you might have noticed, the clever people might have seen that we were growing very fast. We're still growing exponentially, but that exponent has changed. We're not growing as fast. We're not. The radio power leaving the Earth is still going up, but maybe, as your question alluded to, that maybe eventually Earthlings will not be sending so much stuff out into space. Maybe we'll be more efficient about it. We'll go to very directed communication with, fibers and right now these television signals are broadcast every which way, which is kind of a waste of power. And then, as you pointed out, we're going to broadband communication, kind of spread spectrum communication. Those kinds of communications, as you pointed out, are much harder for us to detect. The narrowband, original kind of TV broadcasts, FM broadcasts are relatively easy for us to detect. If they're all doing spread spectrum, that's going to be a hard thing for us to find. Of course, if they're doing it deliberately, then they're not going to deliberately kind of spread their signal out over lots of different frequencies. So radar signals, on the other hand, will probably be kind of a lot of power at one frequency. Maybe they'll have some kind of thing that looks at their spacecraft going around their planet or making sure that asteroids aren't going to smash into their planet or something like that, some kind of radar thing. That might be easier to detect than this advanced communication that you're asking about, which could be very hard for us to detect.
Thank you.
3 more questions. Go ahead, please.
Got in under the wire. I was wondering, earlier on you talked about scanning galaxies, and that really surprised me because it seems like they're very far away. The signals will be very, very faint. What's the rationale for doing that versus just focusing on our own galaxy?
Yeah, that's a very interesting question. Should we look at kind of the nearby stars because the signals are maybe stronger, or should we look at more distant things? The advantage of looking at something far away like a galaxy is that there are a few 100 billion stars in a galaxy. So just in one telescope pointing, you look at 100 billion stars, but then the signals have to be much stronger than the nearby stars. So this is a question about how advanced civilizations are, and are some very advanced and are some not so advanced. Maybe they're just emerging like us. We don't know the answer to that question. So some people think we should look at far away things, look for the very brightest advanced civilizations. Some people think we should. If you look at if you look out at night at the stars, the brightest stars are not the nearest stars. It turns out, because some stars are much brighter than other stars, it turns out that the bright stars in the sky are not nearby. It's just because, although they're these incredibly bright stars, thousands of times brighter than our sun, they're much rarer, but those are the ones that are the brightest stars in the sky that are much further away than the nearby stars. The nearby stars tend to be very dim, and some of them are just, you can't even see them even though they're really nearby. They're just way dimmer than the sun. So ET might be like that. Maybe the first thing we find will be a super advanced, super bright, powerful civilization that's way far away, or maybe it'll be in our own backyard. We don't know.
Thank you very much for the talk. So assuming if we don't hear anything from ET in the next 5 to 10 years, there's a bunch of people saying that we should send out microsats. Yuri Milner saying, all right, let's just throw hundreds of thousands of these like thumb-sized satellites. My question is, should we go for things that, systems where someone thought it was a Dyson sphere, or someone, the TRAPPIST thing where there's just a bunch of potentially habitable planets? What are your thoughts on how do we target?
Yeah. I wish I knew the answer to that question. My personal philosophy is that we don't know what the right thing to target is. We used to think that we should target nearby stars that are like our sun. We call them G-type stars that are a few billion years old. But now we know, just kind of recently, that there could be planets going around the most common kind of stars that are much dimmer than our star, these dwarf stars. And the TRAPPIST planetary system that was just discovered has 7 planets going around this little dwarf star. And 3 of those planets are good. So now I think, and some people also agree with me, that we should be targeting lots of different kinds of stars and not just stars that are just like our sun. That it may be naive to think that you have to have something just like Earth and just like our star to get life started. And so I think the best strategy in SETI is a multiple strategy. Don't put your eggs into a lot of baskets. Into one basket, look for infrared signals, radio signals, different kinds of frequencies, different kinds of signals, lots of different targets, because it's very hard to anticipate what another civilization might be doing. And an example of that is the experiments that I showed you that were dreamt up 200 years ago. Now we think that's silly, you know, why mirrors and smoke signals and stuff like that. And so if you ask me 200 years from now, it might be something, maybe people will be laughing at what I was talking about right now 200 years from now. So you got to kind of think outside the box and try a lot of different strategies. It's my kind of personal philosophy on that.
Thank you.
I think we have one more question.
Thanks for the talk. So you mentioned that for the next 10 years, the LISTEN project, you would be using telescopes in 3 different places, one in the Lick Observatory, one in West Virginia, and the other one in Australia, and also the array of telescopes in South Africa. So is there any plan to build an array of integrated telescopes located in different parts of the world that would talk to each other and also scan different parts of the sky?
Yeah, that is an interesting question, because this problem of radio frequency interference is getting to be this radio pollution coming from our civilization is getting to be harder and harder. So we think that one of the ways to solve that problem is just what you said. If you have 2 observatories far away from each other, maybe on different continents, and they're both pointed at the same star, and both of those observatories pick up the signal, then we can be pretty confident it's not from our human civilization. That kind of experiment where you have 2 different telescopes it's kind of an expensive thing to do right now. It's a tricky thing to do, but it's something that I think we're going to need to do. And one of the next experiments we want to do in SETI is use this thing in South Africa that's made of lots of telescopes, and we can begin to kind of do that. Although it's not widely spread across different continents, it is spread out over many kilometers, and that'll help us figure out what's interference and what might be a candidate signal from another civilization. So I wanted to thank you, and I wanted to say that if you have more questions, I'm happy to answer them informally if you want to come up. And somebody asked about other breakthrough projects and mentioned this Starshot thing. This is another thing that the Breakthrough Prize Foundation is funding, which is this idea that you could get to a nearby star, in this case Proxima Centauri, the nearest star that's 4 light years away, and you can do it by putting a sail in space and using this very powerful laser to propel this sail. It's about 4 meters across. You put this incredibly powerful 50 gigawatt laser on that sail for about 2 minutes, and during those 2 minutes it accelerates to 20% the speed of light, and that means you can get to the nearest star in 20 years in your lifetime and send back images of exoplanets on the nearest star. So that's called Starshot. That's a very exciting new program. Don't hold your breath on that, but it's a fun new thing. Thank you very much.